Welcome to today's lecture. We are still talking about discrete systems with multiple degrees of freedom, and now we are looking at a special type of excitation, base excitation. We already know from base excitation when we were discussing single degree of freedom systems, but we will see that especially when we are talking about multi-degree of freedom systems, in this case 2-degree of freedom system, harmonic base excitation, to my opinion, is much more interesting than those types of excitation that we've seen so far. So when we are talking about harmonic base excitation, then we've discussed that already in previous lectures when we were dealing with single degree of freedom systems. And from there, I have derived that base excitation is still a harmonic excitation, and the frequency of the excitation, the angular frequency, is dependent on the velocity and the length of the excitation that you can see here. So that these are the main parameters, and from there we get omega. Obviously, as you can compare, omega, the angular velocity, is equal to v times 2 pi over the length L. And this is typically what such base excitation can look like. Here we are talking about slow driving on a very uneven road. The length of the bumps that you see here is 30 centimeters. So the length, for instance, could be from here up to here. And the amplitude would be from here up to here, 5 centimeter. That's quite a nasty road. If you try to drive much faster than 5 kilometers per hour across such road, you will really feel like this is a very bad road. Okay, now let's look at Newton and Euler formulation. And obviously we can do that by again using the free body diagram. And if you look at the free body diagram without yet taking care of the forces, how they have to be calculated, then you will see that this free body diagram is exactly the same free body diagram as in case of unexcited motion. And the only difference now is that the forces involved also include consideration of the excitation, which we can express by the coordinate s. But otherwise, the formulas that you see here, we've already seen these formulas in week 4. Okay, so now let's look more closer into the forces involved. And obviously, we can sum up the forces to look at forces at the rear of the car. We have spring force and damper force. And now you see that the formulation of these forces differs from the formulation that we have seen in the non-excited case. Because in the non-excited case, we didn't have the coordinate SR and we didn't have the velocity SR dot. Likewise, we can also have a look at the forces in the front of the car. So again, we have spring forces and damper forces. And if you look at these two equations for the spring force and for the damper force, there's not much difference to the first two, only the indices for R equal to rear have changed to F equal to forward. Now we can also formulate the excitation on the front and rear wheel. On the front wheel we have the amplitude times cosine omega t, and the first derivative that we get here is minus s roof omega sine omega t. Likewise, we can formulate the excitation coordinate SR at the rear of the car. And here we have to consider that the formulation of that excitation is dependent on the formulation of the excitation on the front, such that we have phase angle between the excitation in the front and the excitation of the rear. So it's minus delta psi. That is because if the front wheel hits a bump, then it takes a certain time for the rear to hit exactly that same bump. And this time delay, and here it is expressed by an angle, is through this equation LF plus LR, and you see LF plus LR in fact is the wheelbase of the car divided over L. L, we've seen that before, is the length of the bump, and we have to multiply by 2 pi. And from there we can reformulate SR, and we do that by using the addition theorem for cosine omega t minus delta psi. Why do we do that? Because later we want to collect on the one side for cosine omega t, and on the other side of we want to collect for sine omega t. And of course, once we have SR expressed through cosine delta psi and sine delta psi, we can also come up with the first derivative, which we need in order to determine the rear damping force. Okay, now let's get back to the equations of motion as we have derived it for lecture 5.1, and obviously the left-hand side of that equation remains the same, independent of the type of excitation, but our excitation vector h on the right-hand side will be different now, and so we can identify the mass matrix, the matrix of damping forces, and the matrix of spring forces. So we know about M, K, and C, and the excitation vector H can be formulated according to the equations of motion that we got from the free body diagram, what we got on the right-hand side, and also from using SF dot, SR dot, SF and SR in these equations. Okay, so this is the excitation vector, and of course we have to use now what we found for the excitation SF and SF dot, same as SR and SR dot. And in doing so, well, in fact it's quite a lengthy vector. Don't be puzzled here. It looks like it was a vector with 4 elements, but the first 2 rows is just one complete calculation for the first element of that excitation vector, and third and fourth row make the second part of that vector. Okay, we have discussed about this vector just on the previous slide, and now the question is, how can we make things a little bit easier, because this vector really looks somewhat nasty, and obviously it makes sense to collect for cosine omega t and for sine omega t. So we can express the vector h as the sum of a cosine part, so we have hc times cosine omega t, and we also have a sine part, which is hs times sine omega. So obviously we have to fill the elements hc of hc and the elements of hs to find a nice expression for h. And first of all, we look at all the cosine terms, all the terms that are related to cosine. So we have 1, 2, 3 terms that are connected with cosine omega t in the first part of the vector h, and we have similarly also 1, 2, 3 elements connected to cosine omega t in the second part of the vector h. So finally what we find is this is the vector hc, and you can just follow and see here are 6 terms connected with each other that we need to have, and obviously it looks very similar for those terms in the vector h that are related to sine omega t, and in the first part we have 3 elements and 3 elements also in the second part, and this will give us the vector hs. So what we already see now is a major difference to what we have seen when we dealt with the simple force excitation, direct force excitation, because in those cases that we investigated, there was never an sign-related term, so the term Hs was always 0, and now we have two distinct non-zero parts, one for Hs and one for Hc. So finally now we get H star as the combination of the cosine term and the sine term, H star in complex notation. Well, and after we found H star, then obviously everything is the same again. From lecture 5.1, we know about the frequency response matrix F star, and we know that the frequency response matrix F star projects the input to the system, which is the vector H star, onto the output of the system, which is X star. And we also know that F star is found through the inverse of a complete matrix, which is minus omega square times mass matrix plus j omega times the damping matrix plus the stiffness matrix. So this is nice to do, especially as we've seen from previous lecture if you do that in Matlab. And then of course we also know that H star is expressed by the formula that you see here through the elements, the vectors Hc and Hs. And this is just a repetition of what we've seen for Hc and Hs. And of course, once we have X star, we can also find the vector made of xc and phi c. The cosine part, the sine part is xs and phi s. As we've already seen in previous lectures, the cosine part is related to the real part of X star, and the sine part is related to the negative imaginary part. And from getting xc, xs, phi c, and phi s, we can formulate through the square roots x roof and phi roof. So obviously this allows us again to draw a frequency response diagram, and that's what you see here. Again, this frequency response diagram looks different to the previous ones. So talking about frequency response diagrams, there are a lot of different diagrams that we can look at. It, of course, what we see here depends on the type of excitation, but of course it also depends on the parameters. And the parameters that were used here are the same parameters that we have used for the previous frequency response diagrams. But as I said, the excitation is different, and therefore the frequency response diagrams are also looking different. And I think I don't really have to explain again that the black line is showing the vertical amplitude X roof, and the red line shows the pitch amplitude phi roof. Okay, and I was already mentioning videos. We have seen 2 videos, and now a third one showing the base excitation. And to my mind, this is the most interestingly looking video, especially if you look on the left-hand side of the equation where you see the motion of the system. And again, we see that after some time, we have a steady state for both amplitudes. In the beginning, we see that there are some effects from the initial conditions of the system. Enjoy machine dynamics with MathWorks.